Got it?
It's here. Okay, thank you everyone for coming for this special origin seminar, and thank you for waiting. Today we have Nicolas Kurtovic from Max Planck, who's still PhD student of Polarpedia.
Yep.
So we'll talk about planet formation across different stellar environments. The floor is yours.
All right. Thank you very much. Hi everyone in Zoom. Today I'm going to talk about some of my thesis work, which is related to observation of planet formation. My advisor is Paola Pinilla. I also collaborate a lot with Miriam Benisti, but there's many collaborators that have helped me in the projects that I'm going to show that I just can't put them all in there, but you can check on my reference too that I will be showing. So before I get started with the planet formation, I just want to talk a little bit about planets. So the animation that I'm showing there is an animation of all the exoplanetary systems that we have detected, well, in the solar neighborhood, as you see, but also the bright patch that you saw at the beginning is the patch of Kepler. And so basically, when we look at stars, if we look at them with high enough sensitivity and for long enough time, at some moment we start detecting the planets. It looks like planets are everywhere. And so probably if almost all the stars have planets, it means that all of the stars must have gone through planet formation at the beginning. And so my work focuses on trying to understand how is planet formation different when you look at different stellar environments. So for example, we already know from adult stars that when we look at their planetary systems, it looks like in the M-dwarf regime, the planet occurrence rate is much higher for short period planets. And so if we look at this might be telling us something about how those planets were born or how was the initial disk of the system, the disk from where the planets were born. Now, talking about disks, that is exactly what I do. I take observation of disks and I try to see how the distribution of the material is shaping the future planetary system that will live around that star. And so what I'm showing there, if you are not used to seeing images of ALMA, that animation over there is showing you the dust distribution around the stars that are extremely young in this case. These are stars that are between 1 or 2 mega years old. With ALMA, you can't see the stars. You can only see the dust that is around the stars. And then you also have the solar system for scale. And so my work focuses on trying to understand how is planet formation different when you go through different stellar masses, how is planet formation different when you let time pass by, both in years and also in mega-year scales, and also how is planet formation different when you have more than one star in one system. So over these years, we've been working on many different projects, and I don't have time to show them all. I'm just going to focus on these three, which are like representative of these three axes that I just said. And if you have any other question about other things that I have done, you can always contact me at my email. So I'm going to start talking about what happens with planet formation when we have more than one star in a system. And particularly, I'm going to focus on circumbinary systems. So circumbinary systems are systems that rotate around two stars. So for example, if you are followers of the Star Wars saga, you might remember the planet of Luke Skywalker. So Luke Skywalker used to live in this planet that orbits around two stars. So that would be like a circumbinary planet or a P-type planet. Now there's something important that you should know about circumbinary disks, and is that when you have a circumbinary disk, you can't have a non-eccentric disk if you have like these two binaries in the middle. The simulation that you see over there are hydro simulations for circumbinary disks. The white patch that you see at the center is just the region where we didn't simulate. And then the cavity is the cavity that it's formed around the two central stars. And you can see that even for different binary eccentricities, there are some properties of the disks that change, but they are still eccentric. Okay, so that's something important to know. Circumbinary disks will always be eccentric. Now, since we wanted to understand how is planet formation, for example, in circumbinary disks, we went and we took a circumbinary disk that had an extremely deep observation. So this disk over here is called CS-CHA, that you see over there in yellowish. And then I also combined this image with a sphere image. So you can see actually the two binaries inside the cavity. Now this disk has this very, very high sensitivity observation. Here I'm comparing the exposure time to some other known observations. If you are not familiar with some ALMA surveys, here I'm showing two surveys, which are MAPS and DCHART. These are some of the most successful high angular resolution surveys. And you can see that they are only a fraction of the exposure time of this disk, which is actually, well, it wasn't intended to have such a long time, but we can talk about that later. And so since we have this extremely high sensitivity, we can go and we can try to extract even the finest details from what's happening in this disk. So what I do usually with any system that I'm studying is that I go and I try to model the emission in the visibility plane. In this case, I am showing you the best model that I got for this configuration. This is a model where I was just trying to recover one eccentricity for the whole disk, because we know that these disks are eccentric, and so I wanted to constrain it. But you can see that when I try with just one eccentricity, the residuals are very structured. And then in this other case, I was still trying with one eccentricity with a little bit more complex structure, but one eccentricity was still not doing the work. You can see that in the inner part of the disk, I have in the north, like an over emission, and then in the south, I have like under emission. The problem is that when I go to the outer part, this pattern is flipped. And so I have under emission in the north and over emission in the south. So these like under and over emission, they're usually because you are extracting a model that is not at the right position with respect to the observation. The problem here is that I would have to shift my observation north in the inner part and south in the lower part, in the outer part, sorry, which is not possible. You can't shift emission in two different directions at the same time. And so what we tried at the end was, what if the disk has a different eccentricity as a function of radius? And actually, that solved these structural residuals that we have. And now we only have some low contrast, non-axis symmetric residuals left in the disk. And so here I'm showing you the image from ALMA of after reconstructing it from the observation. And this is the best model for the observation that we got. Now, since the model is parametric, we know exactly all the properties of this model. So for example, we know exactly what is the eccentricity as a function of distance. And there you can see that the eccentricity is actually pretty low. In the inner part, it's just 0.04, and then in the outer part is half of that. And for reference, the eccentricity of the Earth around the sun is like 0.015. So this is really low in eccentricity. And actually, it's like really low for what you would expect for a circumbinary. So now, what is this telling us about the planets that are being born in there? Well, for example, if you form a terrestrial planet around a circumbinary, for example, like Tatooine from Star Wars, those planets start following the eccentricity of the disk. And so terrestrial planets around in a circumbinary orbit will most likely be as eccentric as the initial disk where the planet was born. However, if you put a gas giant in there, the gas giant will start carving a gap in the disk, then it will start migrating. This gap will merge with the cavity, and so you won't see the location of the gas giant. You will just see one cavity that is carved by the two stars and by this gas giant, and the gas giant will shield everything that is outside its orbit. And so therefore, outside of the gas giant, the eccentricity will be much decreased. And so we run simulations to test this hypothesis. Here I'm showing you in the upper row simulations of circumbinary disks without a gas giant, and then in the lower row, it's the same disks, but now with a gas giant. And you can see that the cavity is much more circularized. And it's not just the cavity, it's the whole disk outside of the gas giant orbit. Now, eccentricity is not the smoking gun to find a gas giant in a circumbinary disk. Actually, you can temporarily achieve low eccentricities in a circumbinary disk if you have like, certain physical parameters for the disk and for the binaries. However, you can't achieve axis symmetry and low eccentricity without the need of, without the presence of a gas giant. And so it seems like the combination of those two parameters in an evolved circumbinary system would tell you that a gas giant must be already formed in there. Now, if we look at, for example, some properties of the cavity, here I'm showing you the eccentricity of the cavity for a disk that has no planet and when a planet is included, and also the size of this cavity when you have no planet and when you have a planet included. So you can see that the eccentricity is much more decreased when you have the planet, and then you can achieve the low eccentricity that we're observing, for example, in CSCHAP. However, if you look at the cavity size, you can see that the cavity size barely changes between the no planet and the planet scenario, meaning that the cavity size is not a good tracer to find planets in these systems. Now, this is just hypothetical, but it could be that when you look at circumbinary systems, there could be a population of circumbinaries that are more circular, more axisymmetric, because those are the ones that host giant planets in the inner part of the cavity. And then you could have another population of disks that are less axisymmetric and that are more eccentric because they don't have such giants. Could be. And so, yeah, that's just the first example I wanted to show. So just like as a little summary, that is more or less what I do. I usually take a system and then I try to study all the details of it to get as much information as possible. So in the same way, we also studied what happens with planet formation when you go to very low mass stars. And this one, I'm just going to show it very quickly because it's a paper that it's been getting like a bit old. It's already from 2021. So I'll just show you the highlights of this work. So first of all, you need to know that disks around very low mass stars are much more compact and are much more less massive compared to their counterparts in moderate or in higher mass stars. Meaning that from the observations, we already know that these disks have less material to form planets. From the theory, on the other hand, we also know that these disks also have a much tougher time keeping the material in the disk and not accreting it to the star. And that's because the dust radial drift is much stronger in them compared to moderate mass stars. And so it looks like neither from the theory or not from the observational side, like anyone wants these disks to form planets, but they do form planets because we have detected, for example, planets around TRAPPIST-1, right? And so what we did is that we went and we observed the brightest disks around very low mass stars, meaning the most massive disks, at least in dust content, just to see what was happening with planet formation in those systems. And this is what we obtained. So we don't have the highest possible ALMA angular resolution, but it is still fairly high. And you can see that in the disks that are more extended than the angular resolution, we do detect structures. We have cavities and we also have a ring in this system over here. Now, we don't detect structures in the disks that are more compacted than our angular resolution, but it seems to be like substructure detection is just dependent on the sensitivity and the angular resolution that you have. So probably if we just push the angular resolution a bit further, we would start seeing some structure in there. And now you have to remember, it's not that structures in disks means that we have planets. But we do know that planets create structures. And so that's where we try to make the link. Now, the systems are all fairly compact. So you can see that we have some that are a little bit more extended, that, for example, Neptune orbit from the solar system, and the others are even smaller. Now, the thing is that when we compare the brightest disks around very low mass stars to the brightest disks around moderate or higher mass stars, you can see the difference, not just in the extension, but also in the amount of material that you can retain there. And so one nice result that we get is that even these very compact and very small disks are still structured when you have high enough angular resolution. But it seems like their planetary architectures will be different, like from the very beginning. It's possible that these disks are just born smaller compared to these older that are huge. It's something to be tested, but definitely dust radial drift is playing a role in here, taking all the material from the disk and putting it really close to the star. All right, so that's what happens with what's happening with planet formation in very low mass stars. And now I'm gonna take you to the last project that I'm gonna show today, which is in the time axis. So this is still binaries, but you'll see why it's related to time. And I got interested into this time domain when I worked in PDS-70. So this is the observation of PDS-70 at the first planet that we confirmed that was being born around a young star inside the disk, actually. So you can see there, the planet, it's inside the cavity of this disk. And what we did is that we ran an MCMC to try to find what was the position of the planet in the visibility plane. And so what you see here in the left is all the possible positions. So this is basically a probability density distribution. And you can see that this was the position. I'm gonna put the mouse right at the center of the distribution for 2017. And when you compare it to 2019, you can see that the distribution shifted a little bit. Now this is still within the confidence levels. We don't have exactly the same sensitivity for both observations. So that's why this one is much better constrained than this other one. But that movement that you see over there is consistent with the planetary orbit. And so I thought, okay, so in a year and a half, you can already see changes in these disks when you look at them with high angular resolution and with high sensitivity. And so then I thought, okay, why don't we try to apply this, possible time changing in maybe in a binary. And so we are studying this binary system that is, it has been known for a long time, because even back in 2006, with IRAM, we were already able to detect that there was like an arc of material in a bright 12 CO emission. And so then in 2015, you can see here that with an SPH simulation, in the paper from Dai et al., they showed that this arc of material that was detected was probably from an interaction between the two disks. And of course that we went and we observed it with ALMA, and this was published in 2018. And when I say we, I mean the community. And so you can see here in 2018, the arc of material was redetected, but they also detected all these other clamps of emission like over there that are not directly connected to the main arc. And it was a bit puzzling to see what was going on with them. So when we look at the system in dust continuum emission, you can see again, even in 2006, the dust continuum emission could be detected from the two different disks. Then with ALMA, they were redetected, of course, at much higher sensitivity, but the angular resolution was still not enough to see inside the disk. And it wasn't enough in this survey either. And so what we did is that we went and we observed this disk again at very high angular resolution to see what was happening inside the disks. And this is what we got. So here you can see the two disks. They are separated by about 230 AU at the time of the observation. The secondary disk, as you can see here in the right, it has a ring somehow, and then if you look at their brightness temperature, you can see that the brightness temperature of the secondary disk is much lower compared to the primary. So the secondary disk, for example, it doesn't reach 20 Kelvin in 20 Kelvin of brightness temperature in any part of the disk. So obviously this is not just something about like temperature of the midplane, but it could also has to do with the optical depth and the density of the disk. But if you look at the older disk, the one located around the primary, you can see that this disk is much hotter in brightness temperature. So actually we almost hit like 120 Kelvin in the center of the disk, and then most of the disk stays over 20 Kelvin, meaning that the midplane, well, it looks like the midplane of this disk might be more dense, but also hotter compared to this other one. So that's interesting. You have like this possible temperature difference. And something that was striking to me is that when I looked at RW Riga A, I couldn't see any obvious structure. I don't see any ring. I don't see any spiral. And I was really puzzled at the time. So I finished the calibration. I made this like last final image. I saw nothing. And I really didn't understand at the beginning what was happening. I thought it was like maybe like my fault. It wasn't enough angular resolution. Maybe the image was not like high quality. But no, it is not like, that is not the problem. It's like truly the primary disk has nothing. And what I was expecting was something like the spirals, for example, that we published in 2018 as part of the chart. There we have two multiple stellar systems, and both of them had spirals. And so I thought like, okay, it seems like the spirals are in all the interactions, but they are not. And so we took a step back and we said, okay, let's take a look at the data that we have to see what's going on. And we have 4 observations at different epochs with different angular resolutions from ALMA, because the baselines of the antennas are different too. So you can see that I have observations going with baselines from 15 to 1 kilometer in this observation over here, which is really high sensitivity, but low resolution. And then we have observations with the extended baselines that go as far as 16 kilometers. And so I have observations with very high sensitivity, and I have observations with very high angular resolution. Usually what we do is that we take all the possible observations and we combine them all so that we achieve a full UV coverage. However, in this case, these are binaries, and we know that binaries are not static. And I already had the experience of PDS-70, and I thought, what if these binaries are moving? And so instead of combining them all to create a super high angular resolution, super high sensitivity image, we analyze them all together, but allowing the model to be different for each one of these epochs. And so here I'm showing you the models that we found for each disk. And the difference for each epoch is that these models can be at different positions, meaning that they also have different relative distances. You can see that the model that we got for the RW Riga B is almost perfect to the noise level. And the model that we got around RW Riga A is very good. I am encompassing most of the emission of the disk, but I still have some structural residual. And the residual actually has a very interesting shape, because if you look at the center of the disk, I have over emission over one axis and under emission over the other at the very center of the disk. And this is the structure of the residuals that you would expect when you're subtracting a disk that has the wrong inclination. So that's interesting. Okay, I'm gonna go back to that. I'm gonna skip this one. Okay, so when we look at the position of the secondary compared to the primary, we see that actually the secondary is not at the same place for every epoch. When we look at 2016, you can see that the disk is located here, and then it moves like towards the right and down as a function of time, and it ends up here at 2018. The disk B is moving relative to A at a rate of something like 3 milliarc seconds per year, which is extremely small. It is so small that you can actually compare it to the pixel size of the high angular resolution survey D chart. So the pixel size is usually like 10 times smaller than the angular resolution of the observation. And so we're seeing changes that are way, way smaller than the size of the structures that you can observe with an ALMA observation. And here I'm also showing the pixel size that we will have for the ALMA large program H Pro, and that you can see that it's much bigger than the movement of the binaries. So this also highlights that when you want to see these extremely fine details, it is really, really challenging to recover them from the images. And it's much more robust to do it in the visibility plane. Now, I know that I've given a lot of information, so I'm gonna do a quick summary. So both disks are extremely compact in dust. They are less than 25 AU in extension. Somehow, RW Riga B has a ring. When we look at the astrometry, we see that B is moving relative to A, and it's possible that their interaction produce some non-trivial structure in the disk around A that we are yet not able to describe. But you can see like more or less where it is going with the different inclination in the inner part. All right, so so far, I've been showing you the analysis that we have done in the dust continuum emission. But what happens when we look at the gas emission in the system? So here I am showing you the 12 CO that was published in Rodriguez et al. In 2018. Now with the new observations that we have and with the new imaging, this is the 12 CO that we obtained. So now you can see that all those clumps of material are not just independent clumps like sitting here and there. They are all part of this complex system of extended emission, filaments, and arcs of material. So thankfully, we have high enough angular resolution to see the kinematic rotation of the disks. So here you can see the rotation in the secondary and also the rotation in the primary. And from the rotation, we can recover the dynamical masses of the central objects. And so we know that the central objects are around like 1.25 and 1 solar masses for the primary and secondary. We also have the relative line of sight velocity between the two systems. So we know that B is coming closer towards us, like at 1 kilometers per second compared to A. So now we have the astrometry, we have the masses of the system, we have the relative line of sight velocity. We can combine that with the historical astrometry of RW Riga B, and now we're able to draw the orbit of B around A. And what we find is that last time that they interacted, it seems like it wasn't an hyperbolic flyby. Last time that they interacted as part of this bound orbit. The preliminary results that I'm getting here, so take them with a grain of salt because it's not final, but the preliminary results that I'm getting is that this system has a period of something like 2,000 years. And since we know its current position, we know when was the last time that they interacted, which was about like 300 years. So now we can already take that time and constrain how much time it took for the disk to stabilize after the interaction. What happened in here, and this is hypothetical because I still have to prove it, but it could have happened that this system started as an unbound interaction. Then in the first interaction, it got bounded. From that first interaction, it ejected the material that you see the farthest away, and then they have kept on interacting. Every time that they interact, the plane of the disk changes a little bit. And so next time that they interact, you eject material in a different direction. And so that's why you see filaments going like in all over the different places. And it's because the disk is changing every time that they interact. Also, if you look at the periastron distance, the periastron distance is actually consistent with the outer radius of the dust emission, which is smaller than the outer radius of the gas emission. So the periastron is smaller than the size of the disk. The last time that they interacted, it's possible that RW Riga B went through the disk of RW Riga A. When it did that, it possibly produced a warp in A. This warp has been stabilizing ever since during these 300 years. So you can only see residuals of the warp in the inner part of the disk. And then it's possible that the material that you see around B is material that was stolen from A. So that's why it's much lower in density, and you see it with the shape of a ring, because it's much easier to capture material in the outer part where the orbits have lower velocities. Now, this is all hypothetical. I still have to prove it in the paper, which is coming. But at least like just getting these extremely fine details in the movement tells you the story of what has been happening in the system. And just so that you can like visualize how small is this movement, 3 milliards per year, which is the movement of B around A, is something like 5 meters in the moon's surface, which is much smaller than the distance between the flag and the lunar module from Apollo 11. So that's how small that's how small are the details that you can detect with high sensitivity ALMA observations. So actually, the thing that I say here is that if the astronauts were bright enough in radio emission, like you could give me ALMA in any configuration, I could tell you exactly where the astronauts are walking to. It's extremely powerful. So those are the 3 examples that I wanted to show you about like these 3 axes of planet formation that we have explored during my PhD. Now, for the future things that I'm interested to see how is planet formation different over different stellar masses, which is a continuation of what we have been doing with the very low mass stars. I'm not going to show you stuff about that one today, but I'm also interested in these other 2 topics, which are how are systems evolving as a function of time, both in human lifetime scales and also in mega-year scales, and also trying to do the same things that I've shown you with the dust emission, but to do them in the gas. So there is actually a project that we're already working with, which is called HPRO. HPRO is an ALMA large program, which is a collaboration between people from Chile, from the US, from Europe, and actually some people here from Arizona are working in HPRO, which are Ilaris Bascucci and Ding Shan that are here in the room. And what we're trying to do is that we want to recover the gas mass of the disks for disks that are different ages. And so then with the gas mass, we will be able to link the physical properties of the disks with the evolution as a function of time when you go from very young in Ophiuchus to later stages in upper scope. Now, this is in mega-year scales, but if you look at years scales, like for example, with the binaries that I showed, we're also working on HT loop. This is one of the systems from DCharp. We are revisiting it because you can see that here the binaries are much closer than the binaries in RW Riga, meaning that potentially the movement between these disks, it's much bigger than in the binary that I already showed. So we're revisiting it. I am supervising with Paola, a student from Colombia, and we've been working on the UV modeling of this multiple stellar system. Another thing that we have been interested in doing is taking observations of the same disks at different epochs and trying to see if we can actually see these brightness changes as a function of time. This is still work in progress, so I'm not gonna go into deeper details. And then when we look at the gas UV modeling side, trying to do the same things that I showed you for the dust continuum, but do them in the gas. I've been developing some tools to get this even like higher or more detailed description of what the ALMA observations are obtaining. So, so far, I've been just playing with synthetic models. So here I'm showing you a synthetic observation of a single channel where I was just trying to see if I could just recover a CPD emission. And you can see that the CPD that I used in this synthetic channel is quite bright. Actually, it's as bright as the brightest part of the main disk. But then when you look at the images with the same angular resolution and same sensitivity of D-sharp in this case, the CPD appears and you can see it if you know exactly where it is. But if you didn't know, it would just look as part of the disk, which tells me that probably we have detected some CPDs in the observations that we already have. It's just that we haven't seen them. So yeah, if you're interested in gas emission around this, just send me a message and we can discuss a little bit more about this. So as I told you at the beginning, I don't have enough time to tell you all the things that we have done and the other interesting results that we have gotten in the other projects. But if you want to know more about them, we also have some research on massive young stellar objects on the CPD that Miriam posted. And if you're interested in comparing simulations to ALMA observations, take a look at the package that I already have public in my webpage that is called Sim. So if you want to know more about any of these things, just check my webpage. That is my name, nicolaskurtovic.com. And now I'm going to leave you with the key takeaway points of the projects that I showed. And thank you very much for your time.
Okay, thank you. So first, any question? Yes, teacher.
Yeah, what is the mass range for the very low mass star disks? You mentioned in the second part of the presentation.
Yeah, that's a very good question. And so when we talk about very low mass star disks, let's think about stars that are like between the limit of becoming a star, which is like 79 Jupiter masses, and then maybe like 120 Jupiter masses, something like that, like 0.12 solar masses, or 0.15, around that range. One of the problems that we saw is that it seems like the estimated masses for the objects are lower than the real masses that they have. And so we had some disks that were supposed to be like 0.15 or 0.1 solar masses. And when we look at the Kepler rotation, they look more like 0.2 or 0.25. And so it's been getting challenging to get like observations of real very low mass stars. One way to solve that problem would be to push for even fainter disks that we've been trying with ALMA proposals. But yeah, it's like in the range like right after brown dwarf and then a little bit more.
Thank you.
Yeah, thank you very much. That's very interesting. I'm interested in RW Auriga. I think you mentioned that the Periastron is smaller than the disk size, but I wasn't sure. Is the dust or the gas?
Oh, it's smaller than the gas size.
The gas.
And is around the same distance as the dust size.
Okay. And then the other part of the question was, do you have when you place these RW Auriga into context, do you see of single stars, for instance, do you see a difference between the ratio between the gas size and the dust size? In other words, is there evidence that the gas disk has been truncated?
The gas size for the system is about like 3 times more extended. So it's about like 75 AU. I would say that if I put it into context with other more or less like solar type stars, they are still small. But I haven't done like the real statistics, so I don't know in which side of real small is located. but they are definitely compact. And then in the dust side, it's much easier to see what is the effect. As you see this, like all the dust migrating inwards. So these binary disks are usually much more truncated compared to the single stellar systems. One of the advantages of knowing that this is a binary is that, for example, we're detecting this possible warp. We also know about warps in other systems, but in those other, they don't have companions. And so this is like the perfect laboratory to test the warp, the warp excitation, since you already know exactly where the companion is. So yeah, I would say that that's some of the difference with single star systems.
Okay, any other question from online audience?
Yeah, I had a question.
Okay, go ahead.
Yeah, I have a question about the CSCHA system.
Yeah.
Because you're saying that that properties are explained by the presence of a Saturn-like planet. However, the CSCHA system is like a triple system, right? I mean, it's a binary system, but there's another star at like 1.3 arc seconds that's orbiting around.
Yes.
But does that impact? Can that also explain the structure?
So just to put it in context, CSCHA has been known since a long time because it has this outer companion that was detected starting with Hubble in '98 and then NAC on Sphere. And actually the initial motivation for the ALMA observations that I have was to detect this companion that here I'm showing with Sphere. Thing is that we didn't detect any emission from this companion. It's okay because ALMA doesn't detect stars, but we don't detect any dust, and we don't detect any gas either. So the blob that you see over there in the gas emission is not even 2 sigma. What could be happening here, and again, this is hypothetical. So we already know that this object, this object over here, we already know that it's an M dwarf that is really shadowy. One of the explanations could be that you have CSCHA in front of the chameleon star forming region, and then you have this M star on the other side of chameleon. And so they have a consistent proper motion, but they could actually not be gravitationally bound. Now, this is just a possible scenario. But in that case, then this companion that we are observing would not be producing any effect, like any gravitational effect on the disk. So that's a possible explanation. And then the other thing is that even if they are gravitationally bound, and there is an M star there that has an edge on disk that is really compact because we don't see it with ALMA, then we don't know what is the line of sight distance between them. And so it's really hard to characterize if this companion is having any effect on the disk. At least I don't think I can see a strong evidence for an interaction in the dust or in the gas, but it's still an interesting thing to explore.
Okay, so any other next question? So I have a question about something you haven't talked about, the massive
young stellar objects.
Yeah, how massive do you actually probe, and then what is the major difference that you see compared to the very low mass objects?
So Paola and I have been getting interested into these massive young stellar objects. She just published a couple weeks ago. It's not actually a MYSO because it's just 2.5 solar masses, okay, but we are trying to move. We're trying to move in the direction of MYSO. So we had some sad story. We had some proposals trying to get a survey on all the young stellar objects that are over 7 solar masses. And we wanted to trace, for example, what molecular lines become more strong or more weak as you go to, even to 40 solar masses. So it's a direction that I still want to move to. And let's see if I get more lucky next year.
Okay. That's interesting. Good luck.
Thanks.
Okay, last call for any question. Okay. If not, let's thank Nicolas.
Sure.
Interesting talk.
Thank you, everyone in Zoom. Thank you all for coming.